Hello everyone, thank you for being here. Today I'll be talking about image completion using sparse probabilistic spin logic network. I have done this work with my advisor, Dr. Sneh Saurabh at the Department of ECE, IIIT Delhi. First, I will briefly explain what the title means. We have used a computational paradigm called probabilistic spin logic or PSL to perform image completion. Moreover, we have proposed a method to sparsify a fully connected PSL network and compared with two of the existing methods in the literature. First, I will briefly explain what a PSL actually is. We are all familiar with the binary digits that forms the basis of digital computation. And on the other end of the spectrum, we have a quantum bit, which is a delicate superposition of state 0 and 1. Now we have something in the middle called probabilistic bits, which are classical entities like bits, but are inherently unstable and fluctuate between both the states. The motivation behind this concept comes from seminal paper of Feynman, where he envisioned that the problem to be solved should define the underlying computational paradigm. And image completion is one of the many problems in AI that requires stochasticity or randomness at its core. Moreover, PSL has a very unique invertibility property, meaning it can operate in the forward and the backward mode. So for example, a multiplier can work as a factorizer in the backward mode. Here we have used this invertibility property to perform the image completion. I have listed the analysis done to perform image completion. First, I have implemented a fully connected PSL network using Boltzmann machine learning algorithm. To perform sparsification of a fully connected network, we have performed a stepwise removal of weights. Second is the binary search algorithm. And the third one is the proposed method of achieving sparsity using information gained from the perspective of information theory. Moving on, link prediction is a widely discussed method in literature in context of probabilistic graphical models. Also, the sparse network is expected to be erroneous. So an error matrix is defined to bound the number of connections that can be removed. Figure on the right shows all the instances from the training and the test digit image set. So partial images are given to the PSL network in the backward mode and network performs the image completion. Since the first two methods are widely discussed in the literature, I will only explain the proposed method. The entire process of generating a sparse network is shown here in the flowchart. At the start, the graph G has vertices V as all the pbits, while edges E is empty. Next, MI mutual information between every possible pairwise connection is calculated using probability distribution of the digit image set shown in the previous slide. The maximum valued MI pair signifies that they have to be connected, and an adjacency matrix indicates the existence of connection between any such pbit pairs. Now the pbits will form new connections based on the degree of any pbit in G. For fully connected network, the maximum value for D can be k-1 for every pbit. The condition here is that all the pbits should have a degree greater than equal to D. If not, we pick a pbit A that has a degree greater than 0 and pick another pbit B and try to find the possibility of connection between them. For A and B, mutual information is calculated given their common neighbors and the adjacency matrix is updated. This process is repeated until the minimum degree criteria is satisfied. Once satisfied, we train the PSL network and calculate the ERMS. The ERMS is the error matrix that bounds the number of weights in the PSL network without compromising the performance. At the start, ERMS will be very high, but it will reduce as we keep forming new connections. So ERMS signals the algorithm to increase the degree D of the pbit in the network. Once ERMS criteria is satisfied, we stop the link formation and the algorithm gives us the final value of the weight matrices. Here only pairwise weight connections are removed as they scale exponentially with the number of pbits in the network. However, if we compare the complexity of the three methods, a stepwise removal of weight method is the most computationally expensive and the complexity of the proposed method is of the order K. A and B shows the training and the test images, and C and D shows the comparison of performance of fully connected PSL network and sparsely connected PSL network obtained from the proposed method. This graph shows the error metric with the number of removed weights. To conclude, sparsity is explored to improve the area budget of the PSL network, performing the image completion. Comparison from all the method is listed here. Although the sparsity achieved from the proposed method is slightly lower than the binary search method, however, considering the performance and the computational demand of all the three methods, information gain method is the best performing. We have only used generic pbit model, and hardware implementation of pbits using MTJs is intended as the future work. To explore the power budget aspect as well, we would like to acknowledge TCS Research Scholarship Program for funding this project. This work got accepted in VLSID Conference 2022. This is my contact information. These are the references I have used in the poster and throughout the slides. This completes my presentation. Thank you so much for listening.